So when we're looking here at our conversion factors, when we go from grams to moles, we always want to use the molar mass. Remember, that's found on the periodic table, and if it's a compound, then it's the sum of all the atomic masses in the compound. And then whenever we go from moles to atoms, we're always going to use Avogadro's numbers, 6.02 times 10 to the 23rd. Okay, and some examples of these going back and forth. Here we see we're starting with 14 grams of carbon, and we want to go to moles. And since we have grams, going from grams to moles, we need the molar mass. So I know that 1 mole of carbon is going to equal the molar mass on the periodic table, which is 12.01 grams of carbon. So we can set this up just like always. We have 14 grams of carbon, and since grams is on top, we'll put grams on the bottom again, so it's just going to be 12.01 grams of carbon. Grams and grams match up, and those will go away. And then we put the other side on top, which is 1 mole of carbon. So when we work this out, we'll multiply the top, so 14 times 1 will give us 14 all over 12.01, which will give us an answer of 1.17 sorry, not times, but 1.17 moles. Okay, and all we do is we divide that out. So we have 1.17 here for moles. We want to go from moles into atoms, so all we have to do is we have 1.17 moles, and that's of carbon, and we know that 1 mole is always going to equal of anything is going to equal 6.022 times 10 to the 23rd atoms. So all we do is we set this up. We can go easily to atoms. Since mole is right here, we'll put mole on the bottom. So we put 1 mole of carbon on the bottom, and we put 6.022 times 10 to the 23rd, and that's atoms. And since it's on the numerator and the denominator, they cancel each other out. We go ahead and multiply this guy out, and we would get 7.04 times 10 to the 23rd, and that would be atoms of carbon. Okay, kind of jumbling on that, but hopefully we can see the work that we did. All right, moving on to our second example. It says how many moles are in 109 grams of sodium chloride. So in the previous problem, we were dealing just with an element, so the molar mass was simple. We looked on the periodic table, but here we're dealing with sodium chloride, which is NaCl. So I need to know the formula of it, and I got that from its name. I just crisscrossed sodium and chlorine with their oxidation numbers, and I got the formula. And what I do with the formula is I figure out, well, how much of each do I have? So I have sodium and I have chlorine. I have 1 sodium, 1 chlorine, and I multiply those guys by their atomic masses. So sodium is 22.99, and we have chlorine, which is 35.45. We multiply those guys out and add them up, and we see we'll have 22.99 and 35.45. Add them up, and we'll have 58.44. Remember, that's grams in 1 mole. So I know that 1 mole of NaCl, sodium chloride, equals 58.44 grams of NaCl. So now that I have my conversion factor, I can set it up. I have 105 grams of NaCl, and I set it up. Since grams is on top, I put grams on bottom, which will be 58.44 grams of NaCl. We see that those cancel because they're the same unit. We'll have mole on top. Multiply it out. It will be 105 divided by 58.44. And we see where we get an answer of 1.80, and that would be moles of NaCl. Now moving on to wave calculations. Now wavelength is the distance between 2 peaks, and it's measured in meters. Frequency is the number of peaks that pass a point each second. We measure that in hertz. And we see that we have the equation for the speed of light, where we have wavelength times frequency, which gives us the speed of light. And we know that the speed of light is going to be 3.0 times 10 to the 8th meters per second. Now guys, looking at wavelength and frequency, we always have to mention the hydrogen emission spectrum. And we know that the hydrogen emission spectrum happens because what we have the ground states of those electrons. And when those electrons absorb energy, they become excited and they shift up to a higher energy level. And when those electrons drop back down, what they do is that absorbed energy is going to be released, and it's going to be released as light. And what we see is that each element has a very specific pattern and a very specific bright line spectrum. So we see that the hydrogen emission spectrum comes by having those bright lines that we can pick out from the spectrum, and we can label it to a specific element. Now, we're looking at frequency and wavelength. What we can see is here we have a very, very small portion of the electromagnetic spectrum, which is this entire thing right here, that is actually visible light. And we see that invisible light we have down here. And one thing we can notice from the chart is that over here we have low frequency, but it's a very high wavelength. And over here we have high frequency and shorter wavelength. So if we're to ask ourselves and looking at these wavelengths, well, the shorter the wavelength, we see the higher the frequency. So we're going to see that the purples are going to have the very highest frequencies, and the reds are going to have the very lowest frequencies, okay? Because the purples have very low wavelengths, and the red has very high wavelengths. Now, talking about the nucleus, and we have the discovery of the nucleus, and talking about it, what we see is that the nucleus contains the protons and the neutrons. And it's very small, packed, very tightly dense space. And we see that surrounding it, which we can see the nucleus is right here, and surrounding it in that yellowish hue is our electron cloud. And now our electron cloud contains our electrons. It contains in this area. Remember, we can't specifically point to where the electron is, but we say that it's in an area, and that area is going to be our electron cloud. And it takes up really the most space in the atom. The nucleus is very small and tight, but the electron cloud is very large. Now, we're talking about the s orbital, and the shape of it, obviously we see it in the center circle, so it's going to have a spherical shape. And then we have the 3p orbitals, and what we see is they combine in a dumbbell shape for us. So again, we have the S, which is spherical, and then we have the P, which is the dumbbell shape. When we're looking at those S, P, D, and S, we see that in the S block, which are over here, there are groups 1 and group 2. We see that they can only take 2 electrons, and that's why they only have 2 groups of them. Now, in the D block, which is the middle of the periodic table, made up of all elements, or all metals, so we have all our transition metals right here. The D block can hold 10 electrons, and we know that it can hold 10 electrons because it has 10 groups, meaning we can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and it has 10 blocks in it. We know that the P block, or the P sublevel, that it's going to have the ability to hold 6 electrons because obviously it has 6 groups in it. And then F can hold 14 because it has 14 groups in it. Now, the rules for arranging electron configurations, we have the Aufbau principle says that an electron occupies the lowest energy orbital that can receive it. So we know that it's going to fill at the very bottom, and we're going to go up to the top. Beginning in the 3rd energy level, the sublevels get kind of mixed up. So we have to follow this order of filling, which we could see in the previous, how we fill the sublevels, and as we go through it, we count it with our blocks. Okay, so we have to follow that rule because it'll fill the lowest energy level possible. Now, the exclusion principle says that no 2 electrons in the same atom can occupy the same place at the same time. The Hund rule says that orbitals of a sublevel are each occupied by 1 electron before an orbital is occupied by a second. If we need help with electron configuration, guys, this is the link to the video that you need to watch. The video's on YouTube. It's the electron configuration part 1. And if you go ahead and take this right here, and if you need extra help on your electron configurations, just download this PowerPoint and go ahead and copy and paste this into your toolbar or into the address bar, and it'll take you to the video for electron configurations. Now, moving on to Mendeleev. Mendeleev was very important to chemistry because he was the first person to publish a periodic table. He recognized that elements had similar properties, so therefore he arranged them in his periodic table. Now, what Moseley did, Moseley was accredited with making our modern periodic table, our current periodic table, and he did this by arranging by the number of protons. So we arrange everything on the periodic table because of Moseley, and we arrange it by order of protons on the periodic table.